Welcome to the course on two-dimensional signal processing principles and practices. We'll continue with the 2D FIR filter design. As we had known the filter specifications now, what are the design procedures used for FIR filters, especially the circularly symmetric frequency response, what we had learned, which is a function of omega 1 square plus omega 2 square. Also, its impulse response is depending on the n1 square plus n2 square. So these h of omega 1 omega 2, which are functions and defined in between minus pi to plus pi. Also n1 n2 is having the function h of n1 comma n2 is function of this n1 square plus n2 square. So from this we can, if you have the response, that is h of omega 1 comma omega 2, the frequency response of the circularly symmetric frequency case he had seen, if there is a tolerance. Suppose here the ripple can be in the pass band or in the stop band also. So that responses, if it is not ideal, then you will have the ripples in the pass band and stop band. Supposing taking the ideal cases, here you have the R is the cutoff frequency in this case. So there is a two shadows shown. One is that one the gray, and another one is white. So here this gray one, which is representing the 1 amplitude 1, and the white one is showing this amplitude 0. So in that case, the first one is the low pass filter, which has the amplitude 1, and the second one is here is the 0. Whereas for the case of high pass filter, this is just an opposite. This amplitude will be 0 here, and the amplitude will be 1 in this case, the high pass filter. So where the cutoff frequency is this, so above the cutoff we have the amplitude 1 in all this region, and here amplitude is 0 for the high pass filter. So considering the 1D, similarly omega c1 is this, then below omega c1 the amplitude is high, and whereas in this amplitude is less. This is a similar extension of the 1D case for the low pass and high pass filter for case of circularly symmetric. So you can see the response of this omega 1 omega 2 is circular. This is having the cutoff frequencies R can be 0.2 pi, 0.1 pi, 0.5 pi, depends on that. This filter will have the amplitudes. And if we take the band pass and the band reject structures of the same circularly symmetric one, so the R1 and R2, it will have two cutoff frequencies, right? 0.2 pi or 0.5 pi, 0.3 and 0.7, and so on. R1 and R2 can be of any value. Here is between omega 1 and omega 2, so it forms a ring. That is the band of frequencies it would pass. Here is the amplitude 1, and this portion, the white one, amplitude is 0, and here as well the amplitude is 0. This for band pass. And since this band stop filter, so only the this particular band of white is going to be stopped, and remaining band of frequencies will be passed at the output. So h of omega 1 omega 2 of the circularly symmetric one has the 1 here and 1 here, and this would be 0. So between R1 and R2, this is the ring, can say band pass and band stop filter structures of whose frequency responses are shown here. So if we take the low pass filter response, which we had done in the previous lecture, h of omega 1 omega 2 is 1 for the omega c less than this, it's omega 1 square plus omega 2 square root, and it is 0 for the other cases, so which is having the impulse response this one. And this impulse response, once we know the low pass filter impulse response of the circularly symmetric, that can be extended to the high pass, and then getting the band pass filter and band stop filter and so on. So here this impulse response of the, suppose h of LP, which we have sent R, we had used it as a omega c in the previous expression. This omega c is nothing but R, which is, and by 2 pi root of n1 square plus n2 square. This is the Bessel function we used of first kind and 0th order. Case J1 here, the R is again the omega c root n1 square plus n2 square. This is an impulse response of the low pass filter circularly symmetric. So the filter response is circularly symmetric if we know this low pass. And how do we get the high pass filter impulse response, where the impulse input delta n1 comma n2 is having the minus h of LP n1 comma n2. So if the low pass filter impulse response is subtracted from the impulse input, our impulse sequence, 2D impulse sequence, then we get the high pass filter response. So this is usually this is well known that high pass filter response can be obtained from 1 minus h of LP. So in the 2D case, this is the impulse response meaning is this. So here we have in the frequency response 1 minus h of low pass filter, that is the frequency response of it. So here we talk in terms of impulse responses. So the impulse, how the impulse response of the band pass and band reject and high pass filters are related to the low pass filter is shown here. This band pass filter impulse response similarly, so it will have two bands omega c2, and this is omega c1 and omega c1. So omega c1 and omega c2, so just replacing this with the omega c2 and minus omega c1 expression. So which has two, one here h of low pass which is having omega c2, and the low pass which is having omega c1. So if we subtract them one from the other, so we get the band pass filter of the circularly symmetric. So this is also band stop can be obtained from the band pass 1, so by subtracting it from the impulse. So delta of n1 comma n2 is 1 minus bph of n1 comma n2. So the case, if we can just take this to the frequency domain as well. So if taking this h of LP and omega 1 comma omega 2, this is going to be 1 minus h of LP omega 1 comma omega 2, and this would be h of omega 1 comma omega 2 for the band pass filter, and the band stop can be obtained from 1 minus h of omega 1 omega 2 band pass. So these are the relation between the different impulse responses of the different filters like low pass, high pass, and band band stop. If we know low pass filter, then we can obtain these responses, or if you design this filter in the low pass filter design, if you know the h of n1 comma n2 for the coefficients, then we can get these responses or these filter coefficients by just knowing the cutoff frequencies. Yep. So it's a Bessel function. As we said, this is a Bessel function of first kind and the first order here. So whereas in the Kaiser window we use that zeroth order, here is the first kind and first order. So if we take the low pass filter specifications like the ones we have done for the circularly symmetric one. So if we have the omega 1 and omega 2, and h of omega 1 omega 2 is function of this omega 1 and omega 2, and the filter specification will have the tolerances or the ripples delta p and delta S in the stop band ripple and the pass band ripple we had seen in the 1D cases. So here as well we can have this delta P, delta S, and the region of support for the RP and RS. So RP is the region of support of this pass band here, and the RS is the region of support of this white one is this stop band, and the transition band in between is that region of support RT, pass band and transition band and the stop band. So in that case there will be ripple in the stop band, that is delta S, which is given here as h of omega 1 omega 2 is between minus delta S to plus delta S. So it will have the small ripple amplitude in the stop band, and the pass band ripple is given as 1 plus delta p to 1 minus delta p. Just the extension, if you recall that for 1D also we did this for h of omega between 1 plus delta p to 1 minus delta p. So this is in the pass band. So it's not ideal, it is ideally like circularly symmetric one will have the ripples over it. We can also visualize this when we design the filter. So this filter specifications are this delta p, delta S, and what is the RP and RS, the region of supports, are the cutoff frequencies. If we know that here, this RP and RS, then we can design the filter. So we have this impulse response. Suppose we have the impulse response, this, and taking the Fourier transform would give the circularly symmetric h of omega 1 comma omega 2, and we can take the inverse Fourier to get the impulse response. We had seen through the equations. So this is the visualization of the impulse response, and that is circularly symmetric one, and take the Fourier 2D for DSFT and get the circularly symmetric low pass filter, whereas this region is pass band and this is the stop band here in the low pass filter. So there is the 2D view or the top view of the filter response h of omega 1 comma omega 2. So the case of design methods, coming to the design method of by knowing the filter specification, what are the design methods applicable for the FIR filters. So one is the window method, with the popular and common method also, and the second was the frequency sampling method, the frequency sampling filters basically, and the frequency transformation method, which is also common. So these three methods, and another one is the optimal filter design. So these are 4 FIR design filter we can use for designing the filters. The one, at least 3 of them we can discuss in this course here. So we take the window method, the first one. So if you recall the 1D case, what we had done, this HD of omega in the case of 1D, the specifications are given for the desired response. Desired frequency response is HD of omega 1, omega 2, and take the inverse Fourier transform. That is the same thing we are going to follow here in this 2D as well. So this is the desired frequency response which is known in the 2D. Either it can be a separable or it can be a circularly symmetric frequency response. So that, and inverse Fourier transform, that is taking the inverse DSFT, get the coefficients of this HD of n1 comma n2, which is infinite, we said in the 1D case. So this is obtained, and then this infinite extent sequence is now to be truncated. So that truncation is done through the window. So the window function can be of here, like the one which we have used in the rectangular or the Hamming or Hanning windows, or Blackman window, Kaiser window, those kind of windows can be used. That is, those 1D windows can be used as, or extended as here is 2D windows, or that we will see that how to use this 2D windows, or exactly 2D window or 2 1D windows, like a separable one. So but the infinite extent of n1 comma n2, as we did in the 1D case, that is truncated by multiplying this window function of w of n1 comma n2 here as well. And then this is symmetric about the origin. So if this is symmetric about the origin, the coefficients what we get is also, that is h of n1 will be symmetric about the origin, and we will have the zero phase or the linear phase filter, and taking the equivalent in the frequency domain. So that's a circular convolution of HD of omega 1 comma omega 2 into the window frequency response, that is W of omega 1 comma omega 2. So this is done, just the truncation is through the multiplication, whereas in the frequency domain it's a convolution. So this convolution is helping in the HD of omega 1 omega 1 omega 2 by the window function, it smoothens it. So the HD of omega 1 is smooth, omega 1 omega 2 is smoothed by this window function, the circular convolution in the frequency domain. So which is the equivalent here in the circular convolution, HD of theta 1 comma theta 2, and W is integrated with respect to theta 1 and theta 2. So this is a circular convolution expansion of it. So so what is the W? What are the characteristics we had learned from the 1D window functions? The same thing is applicable here also for the 2D window functions. Like the main lobe width of the window should be smaller, so that transition width of the designed filter will be sharper, that is small. So the main lobe width and the transition band has the relation of the same, like, I mean, it is proportional here. Main lobe width is small, and if you want to have the main lobe width small, you should have the window length high, right? So the larger window, longer window, and this is one case. And if we have the side lobe level to be smaller, and in case it should be in comparing the rectangular window under the case of Hamming Hanning window. So the smoother the window, and the main lobe width becomes increasing, but the side lobe levels are getting reduced. So that's the same thing we observe here as well. The same window functions, window characteristics, we will use it here. The small ripples and amplitudes, the passband and stop band, due to the small side lobe amplitude, that is due to the smoothened response of the function of the window. So Hamming and Hanning and Blackman and Kaiser, and all of them has give the better side lobe properties or the characteristics compared to the rectangular window, but rectangular window has a sharper main lobe characteristics. So these 2 points needs to be noted. So smaller side lobe will increase the main lobe width, and the transition band may increase. So we need to have the trade-off that we had seen in the 1D case. So similarly here also the same window functions can be used either as a separable window or a circularly symmetric windows. So how do we use this window functions here? There are 2 ways to use that window function for the truncation of the coefficients of HD, that is the desired impulse response coefficients. The first method we get is this W of n1 comma n2. That 2D window function can be a separable one, which is product of two 1D window functions. So that is obtained from an analog window that is a 2D analog window, omega c t1 comma t2, where t1 is sampled with n1, t2 is sampled with n2t, n1t and n2t. Then we get w of n1 comma n2 here. So this omega c, the analog window, also is separable, which can be written as WA and WB T1 and T2. Yeah, so two 1D analog windows. By sampling the analog window, we get this 2D window, and we can have this individual N1 T1 N2 TT as well as separable windows of 1D here. So this is one way to use the 1D windows and get them from the 2D window. Like 1D separable window sequence, this is separable sequence we can see, and then the frequency response is again the multiplication of this, the product of W1 to W2, which are functions of omega 1 and omega 2. Here taking the frequency response of the desired filter is separable. Okay, so the frequencies for HD is separable, that means HD of omega 1 into HD of omega 2 can be written in that case. So if we take and its corresponding impulse response is also separable, H1 and H2, the two 1D filters, and then multiply them, here is the impulse response. So frequency response is separable, so this impulse response is also separable here if you take the inverse DSFT for that. And this one we can have here the region of support of these windows, how it will be if it is a separable window. So the separable window, we had seen that one part in the previous lecture, that is N1 and N2. This is for the impulse response, or the number of samples here. So it is having the N1 sample and N2 samples here. It's a squared pattern, and for the circular symmetric, this is N having the N. Okay, so this is the window in the time domain, or in the spatial domain, what we are talking about. So the previous case we had observed that frequency response case, that is in the frequency domain, omega 1 and omega 2 k1. This is the window function which is having the region of support is this. Otherwise we can say this also having the samples, the window which is having the separable window will have the samples like this, N1 and N2. This is going to be the 7 by 7 window. N1 cross N2 is having the 7 by 7. So circularly symmetric will have the N in this fashion. So it will have the circular pattern. The samples will be of the circular pattern. So that's the difference here between the circularly symmetric and the separable window functions. Window functions are these. If we know these window functions, we can use these window functions for the design to get the W for 1 and 2. And the second method of using the window, that is, the first one is using the 1D windows, and the Huang's method, or the second method of using the windows in the design of the FIR filter, where W of N1 comma N2 is the 2D window, and it is sampled here. And this can be the 2D window is here we can have this from getting it to a WA of t, that is t is t1 square plus t2 square. That means this is obtained, the omega c t1 comma t2 is obtained by rotating this 1D window, that is WA of t, and then sample it. So WA of t, replace this with t1 square plus t2 square root 2. So this is a 1D analog window, making it that rotating, so that you get the WC t1 comma t2. After getting t1 comma t2, get the sampled version. So that the 2D window is obtained. So it's from the 1D in this way, the reverse way. So 1D analog window of WA of t is rotated to get WC of t1 comma t2, that rotated analog window, and then sample it to get the 2D window. So the size of the window, again it is depending on that N, which is going to be N1 square N2 square root, because this is rotated, so that gives the number of samples in it. So the second method of window. So the Fourier transform of it, that window function, the analog window, is that omega 1 omega 2. This is representing the continuous domain omega 1 omega 2, which is giving the g of rho, where rho is omega n square omega 2 square root. This is same as the circularly symmetric one. And how do we get this? From the omega WA at t, that one analog window 1D, and multiply by t with the Bessel function, here t into rho, and where rho is omega n square plus omega 2 square root. So this is integration. We get this window function, the Fourier transform of the circularly symmetric one in this fashion. So where J A, as we know, this is going to be the Bessel function of first kind and zeroth order in this case, that in the window. And G of rho is obtained from the is actually the Hankel transform of W of t. In the design, we'll see the details of this Hankel transform of what is the WA of t. How do we get this? Okay. And this is the procedure. We just get to know the procedure, and then we'll move on to the design. So here the 1D analog window for the examples having this obtained from the 2D windows. So the one is the rectangular, Hamming, Kaiser, the common window functions. What we had learned, rectangular window in analog W of t, where t is less than tau, is equal to 1. So and the Hamming window, similarly, Hamming window equation is known, pi t by tau, 0.54 plus 0.46 cos pi t by tau. It's where t is less than t, otherwise it is 0. Hamming window function. And the Kaiser window, similarly, it's a Bessel function again of the I naught is the modified Bessel function of the first kind, and it is of 0th order. And alpha is the tunable parameter. We had seen this in the 1D commonly used windows also, the window function and the roll-off rate and other things. So this is just used, those 1D analog windows are used in this design as well to get the 2D windows. So here WA of t is made 0 at t equal to tau, and t less than tau it is defined, and it is 0 at this equal to when it is equal in all these cases. So that's just a representation of these different window functions. So now if we know the characteristics of it, like the rectangular window is having the very good main lobe behavior, that is small main lobe. The window width is giving the small main lobe width, and poor side lobe behavior. That means the side lobes have the higher dB, that is minus 13.3 dB, the first peak of this side lobe. So the large side lobe peak, we had seen that. In the case of how this window method or the rectangular window helps in the design. So this rectangular window, especially, it is optimal, and it is giving the minimum mean square error criterion based on that. So what is the desired one and what is the actual frequency response? What are we can say what is the h of n1 comma n2 required, the filter coefficients for the rectangular window, how this error is getting minimized. So the error between the impulse responses of the actual one and the desired one and its square. So if we take this square of it, the summation, the error is computed. So the same thing in the impulse response can be expressed in terms of frequency domain also. So which is going to h of omega 1 omega 2 minus hd of omega 1 omega 2 square integrated with d omega 1, but this error needs to be made 0. So this way the rectangular window helps in getting the error minimum here. So the Hamming window doesn't have the good main lobe behavior, because the side lobe behavior has the smoothening window. This is smoothened one. So the side lobe behavior is having the less amplitude, but the main lobe width increases in the Hamming window. We had seen that. And also the Kaiser window, similarly, it is a family of windows which involves the Bessel function. Also it has this main lobe and side lobe behavior which is controlled by alpha. So the tunable window, this is alpha can be fixed to have the main lobe and side lobe behavior. So Kaiser window is preferable also, or the rectangular window as in the case of error reduction. So improving main lobe behavior result in poorer side lobe behavior. This is the trade-off. We need to have this. That's what we had chosen the particular window, and increase the number of samples in the window so that the transition width can be controlled, and as well as we can have the side lobe ripples less in the design. So the common windows are given: rectangular window, Bartlett, Blackman, Hamming, Hanning and Kaiser windows, and its functions that is in the N. These are 1D windows. So this is for the reference to use this windows, and the high naught of x is the 0th order Bessel function, where it is defined as I naught of x equal to 1 plus k is varying from 1 to infinity, k factorial with the x by 2 for k whole square. So this x is nothing but this alpha into root of 1 minus n by n by m n minus m by 2 by m by 2, where m is the number of samples which are taken in the window. So using these window functions, the 2D window can be obtained, or we can visualize this with the plot, this getting the 2D windows for the design. So if you take the window method, in this we give response of the window function, that is w of n1 comma n2 and its frequency response. So if you plot it with respect to omega 1 and omega 2, so this is for the separable window. So you can have the omega 1 and omega 2, the window function is this, and you have at the center you can see the ripples in this case. Okay. Similarly, if we take this is the Fourier transform of w of n1 comma n2, and for the circularly symmetric we have the circles over here, and omega 1 0 and omega 2 0, it gives the high peak, that is depending on the circularly symmetric window. Also it depending on the shape of the window. So either it can be of rectangular, this one, or you can have the Hanning window, or you can have the Hamming windows. So in this separable and the circularly symmetric, this is called the circularly symmetric window, W1 and W2 and its frequency response of it. So this is to observe the window response, so that is the window function, how it would look like in the frequency domain, because we will be using that in the design for convolving either this or multiplying the Wn function with the HD, or the product here. So the Hamming window, which you can see that this is the Hamming window, and this one is the Kaiser window, and with the alpha is 1 here, the alpha parameter, the tunable window, alpha is 3, which is little smoother compared to this one. So the Kaiser window alpha, the ripples is reduced in the case of this. These are the responses of the window functions, is to have the idea of for m equal to 8, the number of samples in that is 8. So rectangular will have this sharp main lobe, and Hamming window will have the little larger main lobe, and Kaiser window can be that was tuned, and alpha equal to 1, the smaller ripple here in this case alpha equal to 3 will have the smaller ripples. So the design which is carried out with the Kaiser window, in this procedure, that is getting the HD of response, and then the inverse h of n1 comma n2, and then it has the infinite coefficients, that is infinite extent response, and then multiply that with the window function of 1D Kaiser window, 2 1D Kaiser windows, which has a cutoff frequency of 0.45, that is a low pass filter design, the design it is used, and the h of n1 comma n2, this case is a separable window which has the non-zero samples of 225 for the design. This is the plot which is shown. I'll show you the design also. Supposing taking this 2 to 5, we have this h of omega 1 omega 2, and the response of the filter obtained is plotted over here. So which you can see the ripples at the center only. This is because this is a separable window, and the frequency response is separable as well. And this is a low pass filter which is having 1 in this region, and it is have 0 amplitude here. And the ripples, this can be identified that it's a separable window response or the circularly symmetric response. We can identify that through this ripples which are at the center for separable windows. The same thing can be visualized for the circular window also. So the cutoff frequency used here is 0.4 pi, and the top view or the contour plot of this frequency response, what is obtained through the design is this. So you can see the contour plot as well. Okay. The same design with the case of 0.45 pi and then 1D Kaiser window, and the number of non-zero samples is 193, and this is with the circularly symmetric window. So circularly symmetric window, the design, so the window function multiplied h of n1 comma n2 obtained from that is 193 the samples, and you can see the circular ripples over here, and the contour plot, it not much differences are the only you can see that this is circular compared to the separable one which was squared pattern. Here is the contour plot which gives exactly this circular one in the contour plot. The design uses the omega C1 or omega C as in the low pass filter. This is a low pass filter design 0.4 pi. And for the case of band pass filter and using this separable window, so again the separable window can be observed from the center, that omega 1 and omega 2, and this is the band of frequencies. You can see here this band is the pass band, and here we get it here. Similarly, the contour plot from here. So this is at the center, and this is the band of frequencies. You can say it is passed. So band pass filter with omega C1 as 0.3 pi and omega C2 as 0.75. So this width is here is 0.3 pi, and this is here 0.7 pi. So between that it would pass the frequencies, and the rest of them below 0.3 pi and above 0.7 pi are attenuated or removed from the input sequences. So this is the plot of band pass filter and its contour plot, and the design which is carried out with the same thing with circularly symmetric. So you can see that here as well, and the band of frequencies 0.3 and 0.7 pi respectively, R1 and R2, and the ripples which were observed in the response is circularly symmetric, which can be visible also in the case of contour plot. This is with the circularly symmetric window, H of omega 1, omega 2. So these are for the low pass filter and band pass filter characteristics. If we take the two window types that what we had used in the design, unlike the 1D case where passband ripple and stop band ripple are almost equal, that is 1 plus delta p and 1 minus delta p in the passband, and the stop band delta s is actually depending on the window shape. Actually, window shape, if you use a smoother window, the side lobe level will be reduced, and it's approximately equal in the case of 1D. But in 2D, the observation here is that the passband tolerance is larger compared to the stop band tolerance. That's delta p is larger, the ripple in the passband is larger and to the stop band, and it is 25% for the separable window more, and 50% for the case of circularly symmetric. So separable window is giving little better response compared to the circularly symmetric in the design, but circularly symmetric will have the ripples all over, and the case of separable window will have the ripples at the center of omega 1 and omega 2 only. So that we can observe, but still this designs which one to be preferred is based on the application, and we can use both the filters like separable as well as circularly symmetric one. The passband tolerance is here compared to that larger, and the stop band tolerance by case of 25%. So here this would be more or less equal. It depends on the window shape. Here this is not so in the case of 2D, and we can see this the spatial domain in the windows. This design is 1D. It preserves the spatial domain characteristics because we can say the window function is considered in the spatial domain instead of the frequency domain. So with this, we conclude with the design of the FIR filter for which the window function using the window method, like the same procedure what we follow in the 1D case, is get the specification in the frequency domain and get the inverse Fourier transform to get the infinite coefficient, and truncate that coefficient by choosing the window function or the multiplying that impulse response, the infinite coefficients using the window function. So the window functions here, unlike 1D case, this 2D case would have two different window functions like separable and circularly symmetric, and in the same way the response of the frequency response of the designed filter as well, the separable and circularly symmetric. So it can be of low pass or band pass. The two cases have been shown. We'll continue with the design of other filters using these two types and different window shapes as well in the next lecture. Thank you.